This is the elastic force as a conservative force, part two. I'm going to discuss what we mean by an ideal spring. An ideal spring is first and foremost elastic. That is to say, when you apply a stress to it, it will exhibit strain. It will deform, but deform reversibly, so that when you remove the stress, the spring returns to its original size and shape. That's elastic behavior. An ideal spring also does not transform any energy into thermal or acoustic energy when it flexes. It has negligible mass compared to the objects that it pushes on, and it exerts a linear restoring force according to Hooke's law, as we'll be discussing. We call it a restoring force because associated with its elasticity, the spring's force tends to try to restore the spring to its original length after it's been compressed or stretched. Elasticity means the spring is always trying to restore itself to its original size and shape. And a linear restoring force is related to this linear relationship that we typically see in the stress-strain relationship between for most materials, most solid bodies. This is that linear equation right there called Hooke's law, where the force exerted by the spring on the objects the spring is pushing on is directly proportional or linearly proportional to x, the displacement of the spring, the stretch or compression of the spring. That's x here. That's our linear equation. The slope of it, represented by lowercase k here, little k, also known as the spring constant. We see that spring constant unit-wise is a force over a displacement, so a force over a length. It is non-zero by definition and non-negative, so k is always going to be a positive number. And the units are newtons over meters. Newtons per meter, the SI units for spring constant. Not to be confused with newtons times meters, Newton meters, the SI unit for work. Another notation hazard here is that the stiffness or spring constant of a spring, little k, is not to be confused with capital K, which represents kinetic energy. They're going to show up in the same equations at times, but little k versus big K mean those two different things. So the spring constant is the stiffness of the spring, and it's a number unique to every spring that depends on that spring's size, its proportions, and the material that the spring is made of. So every spring has a different spring constant, K, a different stiffness. X, the displacement, is how far the spring is stretched or compressed at a given moment. So X is a length, again, measured in meters here. Let's illustrate Hooke's law with the following diagrams. Looking over here, suppose I have two different springs to compare side by side. One of them is much stiffer than the other one. So here, the stiff spring might be the one that has thicker coils or maybe a wider diameter to it. That stiff spring is going to have a larger spring constant, K. The softer spring, the one that's easier to compress, is going to have a smaller spring constant, K. So this will be a spring A, the soft one, with the small K value, and spring B, the stiff one, with the big K value. And I'm showing here that suppose both of these springs have the same natural length. Suppose that when they are uncompressed, both springs have their left ends located here, lined up there, so that at the moments depicted, this incoming cart here has compressed the soft spring a certain distance, x naught, and it's compressed the stiff spring that same distance, x naught. Suppose they've both been compressed by the same distance. Now, on this graph here, I've got in darker purple the Hooke's law function, this equation here for the stiff spring. And then in the softer lavender here, the Hooke's law equation for the soft spring. So at this moment, with a positive compression, x naught, we're graphing spring force Fsx versus displacement x. So here's that value x naught. So looking down at our two linear functions, at this moment, they both have been compressed the same distance, the same x naught, but spring A is exerting a smaller spring force, and spring B is exerting a greater spring force. So the same x values, that is the same x naught, the same displacement, but different spring forces. That's our red spring force here. It's going to take much more force to compress that big spring than to compress the soft spring. And likewise, the stiff spring here is exerting a much bigger spring force on the cart than the soft spring is exerting on the cart at the same compression. What this is indicating is that the slope k of each of these functions corresponds to that stiffness. The steeper slope represents a spring that exerts a bigger spring force at a given displacement. Given displacement, bigger force for a steeper slope. So there's our stiff spring, and there's our softer spring right there. That's the connection between slope and spring constant, slope and stiffness. The other feature I want to show here has to do with that restoring force idea and this minus sign that shows up in Hooke's law, minus sign again shown here. This lower quadrant of the graph is represents when the displacement is a positive number. So this little picture here goes along with this quadrant. When the displacement is a positive number, that is, say the spring is displaced to the right, of course the spring is going to be exerting its force on this mass to the left. The spring is pushing the mass to the left because the spring is trying to restore itself to its original position. The spring is trying to get its left end back to this location x equals 0 here. So with this displacement x being positive, the spring force exerted is negative. X is positive, spring force is negative. That's why our graph is down here in this quadrant. Positive displacement, but negative force. That's that minus sign right there. Over in this quadrant, that would be represented by a picture like this one, where, say, the spring is attached to the cart, maybe magnetically clamped onto it or glued onto it. It's attached to the cart. The displacement of the spring is negative here. See, the spring is displaced to the left of its equilibrium position, or its position where it's at its natural length. So the displacement is negative, but the spring is going to be pulling on the cart to the right, pulling in the positive direction. The spring force is in the positive direction because that restoring force is trying to restore the spring back to its natural length. So the negative displacement corresponds to a positive spring force, hence that minus sign once again. It's there to show that the spring force is always opposite the displacement in order to try to restore the spring, restoring force, to its natural length.